What is the length of the curve? F of x equals 2 log root x plus 2 plus root x for x going from 1 to 6. Now, generally speaking, for length of curves, the formula involved is very messy. So very nice functions are ridiculously hard, and sometimes very messy functions, you got a chance, a real chance. And this is in that latter category. It looks terrible, but the derivative is very nice. Now, before I solicit and say, hey, any guesses? Let me ask you a different question. I claim that 2 of these are impossible answers, that they can't possibly work. Which 2 can't possibly be true?
A and B.
A and B. So why do you say A and B?
It's from 6, well, from 1 to 6, 5 long, plus 5 long.
Right. This means you have to go at least 5. And on the other hand, you say, look at these 2 numbers. These are less than 5. So there's no way that those can be the right answers. So that's good. We can eliminate options. And when you're taking multiple choice problems, sometimes elimination can help you a lot. And indeed, sometimes what you do problems is eliminate 4 wrong answers, and whatever remains must be right. So now that we've eliminated 2, it's not a 1 out of 5 chance. So today it's a 1 out of 3 chance. All right. Do we have an answer?
C.
It is C. 3 square root of 3. All right. Good. So what's going on? We have a formula for length. That's square root of 1 plus f prime of x squared. That's why they gave us this f prime of x. They were very nice. They gave us a hint that was useful. Generally speaking, hints tend to be useful. And, well, what happens? You plug in what f prime of x is. And when you square, well, you get rid of the square. So it's 1 over x squared plus 2x. Common denominator. X squared plus 2x on the inside. So upstairs, you get x squared plus 2x plus 1, because the first one here becomes x squared plus 2x over x squared plus 2x. And now it's like, whoa, x squared plus 2x plus 1, that's a square. And when we're dealing with problems with square roots, we're sort of in the mindset, look for squares. And so there we are. It's x plus 1 squared, which becomes x plus 1, outside of a square root. Now, maybe it's not looking too great right now, but you say, I wonder. If you set u equal x squared plus 2x, because when in doubt, look for good substitutions. And x squared plus 2x is inside a square root. That's our function on the inside. Substitution is an inside job. The derivative is 2x plus 2, which is really close to x plus 1. Really close. Now you might say, how close? Off by 2. Now the nice thing about 2 is it's a number. We can deal with numbers. Another way we could have written this du is if we divide both sides by 2, 1/2 du is x plus 1 dx. So that, lo and behold, the x plus 1 dx becomes du times 1/2. This term will become u to the negative 1/2, and make sure you update your bounds. These are x bounds. We want to switch to u bounds. And now we're most of the way there. Integral of u to the negative 1/2, you add 1 to the exponent, becomes u to the 1/2. You're going to divide by 1/2, which means multiply by 2, which gets rid of that. So now it's u to the 1/2 from 3 to 48. And you just work it out. So there you go. There you go. All right. Any questions for that problem? Well, then we can move to our thought for the day. Make sure that you always have the right tools for the job. It's no use trying to eat a steak with a teaspoon and a straw. Now, this is, I've been looking forward to saying this for some time, because I think back to grading the final from last semester it's for Calculus 3. And it was on a particular problem that dealt with sort of the last topic in the course. And I was seeing people throw the craziest ideas at it, which had absolutely no relevance at all. They were just saying, I don't know what to do, so I'll just start throwing out random tools. Make sure that you are using the right formulas. If you're not using the right formula, no matter how much work you do, you're not going to get anywhere. And it turns out math graders are not overly sympathetic. We don't grade based on how much you wrote down. We look for how much is right. And so an important thing to do is to say, look, it's not enough to know how to use the tools. It's also important to know when to use which tool. Make sure you're using the right formula to solve your problem. The wrong formula will just lead you to dead ends. So know your tools. All right. Now, what's our goal for today? Well, surface area. We've been going through geometry. So we talked about volume, and we spent a couple lectures on volume. We talked about length. And surface area is sort of a nice natural extension of length. And so what's going to happen is we're going to take a piece of a curve, and we're going to spin it. And then say, okay, what's the resulting surface area? So it's a very highly specialized case of surface area. And there's our formula, 2 pi radius length. And if you're following along with the formula sheet, that's on our formula sheet right here on the right-hand side. All right, so that's what we're learning today. But that being said, surface area really is a continuation of length. And I want to make sure we get a little bit of practice doing length. And not just that I get to do practice, but you get to do practice. So here's a problem. Find the length of y equals 1/2 times e to the x plus e to the negative x, where x goes from 0 to natural log 2. Okay, so what's the process? All right, we have our formula for length. So we're going to use our formula. So we need to take a derivative. How do you take the derivative of e to the x? Well, we love that one. It's our favorite function, e to the x. Derivative of e to the negative x, got to chain rule that. So it's going to be e to the negative x and then times the derivative of the inside, which makes there be a minus. So e to the x minus e to the minus x. And now we have to square it. So you have a fourth. E to the x squared is e to 2x, e to the minus 2x, sorry, e to the minus x squared is e to the minus 2x. E to the x times e to the minus x, 1. All right, you can think of it as you add the exponents. So there's a minus 2, but secretly it's minus 1/2. You're like, whoa, minus 1/2, and you have a plus 1. It's almost like you have a plus 1/2. So we're switching that middle term from being negative to being positive, which sets us up to say, oh, that's basically like what we had up here, except instead of a minus, it's a plus. So we have a square. And so the square root of a square is nice. So we have 1/2 e to the x plus e to the negative x. So that's what we have to integrate. Well, of course, we integrate. You get e to the x minus e to the minus x. And we go from 0 to log 2. And you plug in, e to the log 2 is 2, e to the minus log 2 is 1/2, e to the 0 is 1. You clean it up, 3/4. All right. Now, bonus fact. This function actually is a very famous function. And you've seen it in places. So if you've seen, for example, this is a rough drawing of the Golden Gate Bridge. This cable here is hanging in a very particular shape. It's called the catenary. And it's this function, 1/2 e to the x plus e to the minus x. It's not a parabola. Your algebra books misled you. It's this function. And it has a name. It's called hyperbolic cosine, sometimes known as cosh. And then if you put in a minus, it's sinh. And so if you recognize hyperbolic functions, you say, oh, there's some nice facts. Derivative of cosh is sinh, derivative of sinh is cosh, and cosh squared minus sinh squared is 1. And you can do everything much simpler using those facts. Now you might say, why are you calling it hyperbolic cosine? That doesn't look like cosine. Or does it? Spoiler alert, it is cosine. Or is it? You'll know by the end of the semester. So there's a fun story to tell. All right. Things to look forward to. So don't drop out. You got to stay to the end. Otherwise, you'll never know. Wait, what's going on with cosh and cosine? I got to know. I got to know. All right. Any questions before we move on? Okay. Well, in that case, we're ready to get to our main event for today, which is we're talking surface area. So, what's our goal? We're given a portion of a curve. Doesn't have to be the whole curve, just some part of the curve. And we're going to spin it. Now, we've been spinning before, but we've been spinning to make solids. These are not solids. They're hollow. These are like vases or vases, depending on how posh you want to sound. And so we're spinning the curve, and we're saying, okay, we've made a surface. What's the surface area? Now, if you think back to our underlying philosophy for integration, our underlying philosophy says, let's break things into small pieces. And if we break things into small pieces, and we understand what's happening with each piece, then life is good. So we say, okay, what are we spinning? Now, we're not spinning strips. What we're going to do is we're going to take our curve, and we're going to break it up into lots of little pieces. Now, what's the advantage of breaking the curve up into lots of little pieces? Well, when you break it up into small parts, each small part looks very much like a line. And so that's going to help us figure things out. So we're going to take a little piece, and we're just going to spin a small part. We're going to say, well, what happens when we do that? Well, when we spin a small part, we're going to get just this sort of strip here. So now I say, look, if I can figure out what's the area of this strip that I've spun around, this little segment, I win. Okay. Well, so what's going on? We have a straight line segment, we're spinning it around, and we see this shape. Now, what can we say about this shape? Well, you can imagine what it looks like. If you were to extend this down and then spin, what would you see? What's the shape? It's a cone, right? So you have the part that you're spinning, and then you have this other part. So we're after just this piece. But we can at least visualize that, yeah, it's like a cone. And so we say, okay, what can we do with this? Well, what we'll do is we'll take out our scissors, and I guess I should make one more comment. You may have seen this particular shape before. It's a piece of a cone. If you've ever had animals who've had to have surgery, they wear that cone of shame. That's the shape. All right. Now, what do? We reach into our pocket, pull out our scissors, and we go, and we cut. So we're going to cut this open, and what is going to happen? Well, I happen to have taken this cone, and I cut it, and this is what came out. And in general, you're going to have what you see here, which is a wedge. So it's a piece of a circle. So what are we after? We're after trying to understand what is this shaded area at the top. That will tell us how to figure out the area that came from spinning. So in other words, what we're after here. Okay, so to get to that, we need to do a little bit of geometry. Okay, we need to understand wedges. Now, you might say, I guess I should point out, how do I know this is a wedge? How do I know this is like a piece of a circle? Think of this part right here as being the tip of your cone. And now, if I think about the cone, from the cone down to this line segment, what's true about these lengths?
They're equal?
They're all equal. But that's the same as if I came here and just went to the end. So these lengths here are all equal, which means that if I think about this as being the center of the circle, then this is the edge of the circle. So it is a proper piece of a circle. It's not just like it looks like a circle, it is a circle. All right, so, and we'll need to refer to that in a second. So, geometry of wedges. Suppose you have a circle, and we're just going to take a piece of it, and we're going to mark a central angle theta. You say, all right, how much area is there in that piece? Well, what we can do is we can think of it as proportional. Say, well, let's look at the area in our piece over the total area. So I'm taking a ratio here. So that's, you can think of it as the percentage of the area that I have in the circle. That's got to match up with the proportion of the central angle. Well, how much does that take up? Well, theta, and then I say a full revolution would be 2 pi. So theta divided by 2 pi. Multiply across by pi r squared, and we see that the area is 1/2 times our central angle theta times r squared. So I can measure the area of a whole wedge if I know the central angle and the radius involved. And I can also measure another thing, which is the length, if you will, the amount of crust on the edge of this slice. So, same principle. I'm going to look at ratio. So I'm going to take just the amount I'm after versus all the way around. That's the circumference, which is 2 pi r. That has to match the angle in the middle divided by 2 pi. Multiply across by 2 pi r. 2 pi's cancel. So if I take the central angle times the radius, that tells me how much length there is along the edge. All right. With that in mind, we're ready to do our computations. See a hand up?
Is that central angle something that will be given to us, or do we have to calculate it?
Ah, there's a question. Are we going to have to figure out what theta is? We won't. We're going to be able to get rid of that. But that's not so clear right now. But we'll see what happens to it. Okay, so our shaded area. Well, what I can think of it is I have a big wedge all the way to the outer part, and then I'm going to subtract out the smaller wedge. So 1/2 area of the big one, so that's the radius is all this big r plus little l, then subtract off the little piece. Okay, that's not so bad. Now what? Well, we channel our inner algebra. What do we want to do? Expand. Okay, so we expand this r plus l squared. And we get 1/2 theta r squared. Okay, that's your r squared. You get your cross terms, you have your 2 times r times l. 2 times 1/2 goes away, so that's where you get your middle term, theta r l. Then your last term, 1/2 theta l squared. And you say, very convenient. These first and last terms cancel. But there's something else convenient. Basically, after we do the cancellation, we say, hey, there's 2 terms left, but one of them is very small. The 1/2 theta l squared. L is very tiny. So we're thinking of L as being Remember, we're cutting into very small segments. If we come back to our picture, when we talk about L, it's this length here. And that's going to become very, very small. And so when you take something very, very small and you square it, it's going to become really ridiculously small. So small, ignore it. Okay, so we say, great, theta r times L. Now, the question that someone posed, well, how do you find theta? That sounds like it's going to be a lot of work. We're not going to find theta. What we're going to do is say, hey, theta r means something. Is there anywhere else where we've seen theta r? Yeah, it looks like this part. So in other words, theta r is showing up over here. Theta times r. Now, where is that showing up in our picture? This part here is coming from this inner portion. Now, this is blown up. Keep in mind that when we get to the actual spinning, these are so close that they're essentially the same. So what am I measuring here when I'm looking at this theta r? What is this capturing? What does it look like?
It looks like a circle.
Looks like a circle. What part of the circle? The circumference of the circle. So what we have is circumference, which is 2 pi, a radius, and a length. Now, what is that referring to when we say radius and length? So here we go. When we take our shape and we spin, what's going to happen is we're spinning this little piece, we spin it around, and we say, aha, this part is our circumference. That's 2 pi r radius, where, my picture's getting a little bit crammed here. But the radius is the distance from where you're spinning to the curve. So that's 2 pi radius is really the circumference that you're forming. And then the length is the little length of the curve. So this 2 pi radius length, that's the area of this little strip. And once you have the area of one little piece, you add them all together. And life is good. So our formula for surface area is adding up integral a to b, 2 pi radius length. So remember, again, radius, distance from the curve to where you spin. Length is the length of that little piece. Now, the length of the little piece will vary depending on setting, but we just learned a setting, which is when you have y equals f of x, then that length is your square root of 1 plus f prime of x squared dx. We'll learn other settings as well, so we want to leave it as generic length so that we can adapt to other situations. Another thing to note is that you can spin around any line, x-axis, y-axis, even lines on slants. And you don't have to change from integrating with respect to x to integrating with respect to y. Only thing you have to do is account for your radius. That's what will change. All right, so there's our formula. Any questions before we do an example?
What's the angle theta? Originally from when we made the cut around the ring, and it became like part of a...
Right.
How did that become 2 pi?
Well, so you have to think the angle theta disappears into the computation. So what's happening is essentially the theta is capturing just sort of what kind of cone you have. So if you have a cone which is very steep and coming in versus a cone which is very shallow, and in other words, you had a cone that looked like this, you'll have different angles of theta. So somehow that's what you're capturing. Now, the problem is computing theta is hard. So we don't want to do that. So what ended up happening is we said, okay, we have an expression that involves theta, but it also involves 2 other parameters as well. Now, theta was hard to compute, but r is also hard to compute. And so we said, oh, now I have two hard things to compute. But their powers combined. When we multiplied theta times r, we said, oh, that becomes this length in here, which is something I can compute. It becomes this length around, which I can interpret as the circumference of a circle. So we got, in some sense, lucky. But that's okay. We'll take it. Anything else? All right. Do an example. Good times. Find the surface area when y equals x cubed, where x goes from 0 to the 4th root of 11, is spun around the x-axis. Now, generally speaking, when you see numbers that look terrible, and no, 0's not terrible, 0's a friend. I'm talking about the 4th root of 11. If you see a really terrible number like that, something's going to happen where that number becomes like, wow, what a great number. So have faith. Don't panic when you see strange expressions. All right, so we know we're looking for surface area. What's a clue that you're looking for surface area? Yeah, we read. It says surface area. And so since it's surface area, we say, look, there's one basic surface area formula. We just have to adapt it. So we write down our surface area formula, and that's going to be our reference as we go along here. Okay, so we have y equals x cubed. We know, vaguely speaking, what x cubed looks like. At 0, it's at 0, and then it's going to go up. We don't have to be super precise. A bad picture can usually be perfectly fine. So let's say this is our curve. So here's our y equals x cubed. And we have here this strange number, 4th root of 11. Where are we spinning around?
X-axis.
X-axis. Okay, so we're spinning down here. And I like to mark that as reference. Okay, so now with this in mind, we have to make a decision. Do we integrate with respect to x or with respect to y? There aren't necessarily wrong answers here. You can do either. However, I tend to be biased, and I say, well, look, how is the problem presented to me? And what does that mean? Well, I'm given y as a function of x. And so when I see that, I look at that and I have a thought. It's like, if I see y as a function of x, then I should go dx. So I should integrate with respect to x. If my problem says, oh, x is a function of y, my thought is I should integrate dy. So since it's presented to us as functions of x, I'm going to stick with x. Okay, so we're going to integrate with respect to x. All right, with this in mind, we can start filling things out. What are our bounds for x? 0 and 4th root of 11, because they gave us our x bounds. 2 pi becomes 2 pi. Yeah, it's a number. All right, now the fun part, the radius. So here's our thinking. We're not taking a slice, we're just thinking, here's a little piece of the curve. So that's what we're grabbing, a little tiny piece of the curve. And now for the radius, what we're going to do is we're going to go straight down to where we spin. So this is our radius. All right, so question. How far is it from this little piece down to the radius? You can say x cubed. Some other people might have been tempted to say y. And that's a fine answer. This distance is y. That measures down to the x-axis. Now, we wouldn't write down y because we're integrating with respect to x. But we say, y equals x cubed. So our radius is x cubed. For our length, we say, what setting are we in? We're in the y equals f of x setting. So our length becomes the square root of 1 plus the derivative of x cubed, 3x squared, squared dx. So this entire piece here, this is including the dx. So the dx is showing up in the length. So now we've gotten our pieces put together. So from here, we just have to integrate. All right. So good times ahead. 0, 4th root of 11, 2 pi x cubed, square root of 1 plus 9x to the 4th. Well, bad news, it's going to be really hard to make the inside look like a perfect square. So squaring, looking for that square on the inside, hopeless, hopeless. You really need at least 3 terms on the inside to make a perfect square. There's only 2. So we can't square the inside, so that's out. So what's our next thing we can look for? Some substitution. What's a good substitution to make here? 1 plus 9x. Why 1 plus 9x to the 4th? What is special about 1 plus 9x to the 4th? Okay, so someone said, you'll end up with an x to the 3rd. Another thing, so that's one thing that's nice. There's actually a second thing that's nice. It's on the inside. So we're looking for functions on the inside. So we'll set u equal 1 plus 9x to the 4th. du is 36. Oh my goodness, x cubed. Now, do we get nervous about the 36? No. We have the technology. So this becomes 1 over 36 du is x cubed dx. So we'll get integral of 2 pi. The x cubed dx will become a 1 over 36 du. And the square root of 1 plus 9x to the 4th becomes what? Square root of u. But we won't write square root of u because that's not calculus friendly. What's calculus friendly? U to the 1/2. When I say calculus friendly, our rules are based on u to a power. All right. Are we done updating? What's left? The bounds. When you plug in x equals 0, what does u become? It is the 1. When you plug in the 4th root of 11, what does u become? 100. Right? Because 4th root of 11 to the 4 is 11. 11 times 9 is 99. 99 plus 1 is 100. Now 100, nice number, easy to work with. All right, so we're ready to integrate. So we get 1 over 18 times pi. U to what power? Three halves. And then in front we're going to have a 2/3. Evaluate 1 to 100. Okay. Well, this should be interesting. So 18 and 2 leaves us with a 9. So we have a 1 over 3 times 9 times a pi. What is 100 to the 3/2 power? Now, if you take 100 cubed, you get 1,000,000. Square root of 1,000,000. 1,000. You can also take the square root of 10. Sorry, square root of 100 and get 10. And 10 cubed is 1,000. How about 1 to the 3/2? It's 1. Okay, so we have 999 divided by 3 times 9 times pi. Sorry, excuse me, 3 times 9 times pi. Okay. Can we simplify anything? Yeah, see how 999? If I take 999 divided by 9, what does that become? 111. Now, can I divide 111 by 3? Yes! What is 111 divided by 3? 37. Wow! In the business, we call that nice. Whole number. Beautiful answer, beautiful answer. All right. Well, we have a few minutes left, so we may not be able to do the whole thing, but let's at least do a piece of this. We have a curve, y equals e to the 2x from 0 to 1. So that looks like this. Here's our curve, y equals e to the 2x from 0 to 1. And we're asked to set up, but not evaluate. Oftentimes, that's the best we can do. We want to go around two lines. One line is y equals -1. The other one is x equals 2. Okay, so part A. We want to do an integral of this that finds the surface area if you integrate with respect to x and you go around the line y equals -1. Our generic formula, we'll just put that down for reference. Integral a to b, 2 pi, radius, length. Now, for part A, what are our bounds? 0 to 1. 2 pi. Now, we want to find this distance, y down to -1. What is that? Well, we can think of it as y plus 1. But if we're integrating with respect to x, what do we replace y by? By the curve. So it's e to the 2x plus 1. Then the length, square root of 1 plus the derivative, 2e to the 2x squared. So that's part A. What about part B? Well, it's the same bounds. It's the same length. What's the only thing that changes? Well, it's the only thing that's left. It's the radius. So now it's that distance. So what's the distance to the line x equals 2? 2 minus x. So it becomes 2 minus x. Now, we have a minute left. We can do the other version. If y equals e to the 2x, take the log, and you get that log of y equals 2x, or x equals 1/2 log y. If we integrate with respect to y, we can do this. We're totally allowed to do this. Well, our bounds will become, we start at 1 and go to e squared, because at x equals 0, e to the 0 is 1. Sorry, not e squared. At x equals 1, it is e squared, because it's e to the 2x. So 1 to e squared. And now, around y equals -1, what's this distance? We called it e to the 2x plus 1, but what else is it? Y plus 1. Square root of 1 plus, what goes inside of here? Because we're integrating with respect to y now. We would take the derivative. Derivative of log is 1 over. So 1 over 2y squared. And for part D, I'll write this down. You can check it later. So it's 2 pi, 2 minus 1/2 log y, square root of 1 plus 1 over 2y squared.